Swayam Prabha. Digital India. Educated India.
We'll talk about another interesting concept about graphs, namely vertex cover. So what's a vertex cover? A vertex cover is a set of vertices. Okay, so it's a set of vertices C such that every edge is covered by these vertices. That is to say, every edge has at least one of its endpoints occurring in C. Okay? So if you think of the edges, remember edges are just sets of size 2, subsets of vertices of size 2. And for C to be a vertex cover, every edge must intersect the set C. Okay, so here's a little example. So here's my graph. And suppose I first, I'm trying to build a vertex cover for this graph. Suppose I include this vertex, this vertex into my cover. That already takes care of all these highlighted edges. So they are all now covered. I need to worry about covering the remaining. So I might, keep going and add a bunch of vertices. So all these highlighted vertices, suppose they are my set C. And indeed, C is then a vertex cover because, so I colored the edges red if there is some vertex. You could think of it as a vertex looking, at that edge. So this, if you place somebody here, they can see these edges. And what we want to make sure is that every edge is covered by one of these people you have placed around the vertices. So all you need to do is place, in this example, 4 people on these 4 vertices, and then all edges are covered or watched by these 4 people. Okay. All right. So vertex covers there are trivial vertex covers. You could just take all the vertices, that forms a vertex cover. Okay. Every edge is between a pair of these vertices. So if you took all vertices, then it's guaranteed to be a cover. You could also take all but one vertices. So you could just leave out one vertex. That is still guaranteed to be a vertex cover because every edge will have to at least, every edge has 2 vertices, so it will have at least one vertex which is not this V. Okay, so these are trivial vertex covers. They're pretty big. They're almost as big as the entire vertex set. The interesting question is how small a vertex cover you can find. Okay? So that's the algorithmic question. Given a graph, find a small vertex cover, or find the smallest vertex cover. Okay? Unfortunately, this is an NP-hard problem. So it's one of those problems that's with rich enough structure that if you could have solved it, you would have solved a whole host of other problems. Unfortunately, it's we believe there are no efficient algorithms when the size of the graph is really large. Of course, if the size of this graph is pretty small, you could try all subsets of vertices and find which ones are vertex covers. But when the size of the graph is large, obviously that's not a good solution, which it's exponential in the size of the vertices, and we believe all algorithms out there are somewhat similarly inefficient. Okay, so it's considered to be a hard problem. However, today we'll see 2 connections between vertex cover and the maximum matching problem that we talked about earlier, which is actually not a hard problem. We didn't discuss an algorithm, but it's one of those problems which has an efficient algorithm, and we will be able to relate vertex cover to this problem. In fact, the relation is pretty tight in the case of bipartite graphs. So for bipartite graphs, finding smallest vertex cover is not a hard problem. It's essentially the same as finding the largest matching in a bipartite graph. Okay, and when it's not a bipartite graph, in a general graph, we'll see that you'll be able to find a vertex cover, within a factor of 2 very efficiently, within a factor of 2 of the optimum very efficiently. So these are a couple of things we'll see shortly. Okay. Okay, so that's what a vertex cover is. And remember what a matching is. It's a subset of edges such that no two edges share a vertex. Okay, so it's a set of edges such that you took any two distinct edges, they are disjoint. So what's the connection between vertex cover and matching? So firstly, I claim there is an easy relation in one direction, that if you find a large matching, that implies that vertex covers cannot be small, they will have to be even larger. So any vertex cover C will have to be at least as large as any matching you find. Okay. So these are two different objects, right? Matching is a set of edges, vertex cover is a set of vertices, but still there is an easy connection saying the size of matching is a lower bound on the size of any vertex cover. So why is this? Well, to build a vertex cover, you need to cover every edge in the graph. In particular, you need to cover every edge in the matching. But to cover every edge in the matching, for each each vertex can cover at most one edge in the matching. The edges in the matching do not share vertices, so you cannot use one vertex to cover, say, two edges in the matching. Okay, so every vertex that you pick in your vertex cover can cover at most one edge in M. So you need at least as many vertices in your vertex cover as there are edges in M. Okay, so that's an easy lower bound saying that the size of matching is a lower bound on the size of the vertex set. So if I had to graphically represent this, so these numbers 0 to n is the total number of vertices in the graph, and what we are just saying is that if you were to plot the possible range of values that the vertex cover sizes can take, right? So remember I already mentioned there are trivial vertex covers of size n or n minus 1. Similarly, there are trivial matchings of size 0 or 1 in a non-empty graph. And you can keep finding maybe larger and larger matchings, and every matching you find, you're guaranteed that there is no vertex cover smaller than that matching. So the possible size of matchings are in some range 0 to the size of the largest matching, and possible sizes of vertex covers are in the range size of the smallest vertex cover to n, and the size of the smallest vertex cover is greater than or equal to the size of the largest matching. Okay. Now, I promised you that in the case of bipartite graphs, there is a tighter relation, and that is Koenig's theorem. So Koenig's theorem says that in a bipartite graph, actually, this gap doesn't exist. The size of the smallest vertex cover and the size of the largest matching are equal. Okay, so the interesting direction to prove is that whenever I find, if there is a vertex cover of a certain size, the smallest vertex cover is of a certain size, then actually you can find a matching all the way to meet that vertex cover. We already, I've stated it as the matching is at least as large as the vertex cover. We already know that the matching cannot be any larger than the vertex cover. So all it remains to prove is that I can find a matching which is at least as large as the smallest vertex cover. Of course, if you took a vertex cover here, I won't be able to find a matching which is as large as that vertex cover. But if you took the smallest vertex cover, Koenig's theorem says that you will be able to find a matching that is at least as big as that vertex cover. In fact, it will be exactly as big as that vertex cover. Okay. You could also prove this same theorem. So I'll prove this in a second. You could also prove this by showing how to turn a maximum matching into a vertex cover, right? So there is an efficient algorithm for doing that also, to turn a maximum matching into a vertex cover, which is at least which is no bigger. But we'll see there's a much simpler it is a simpler argument using Hall's theorem to build a matching than to build a vertex cover. So let me show you that. So suppose you're given a bipartite graph xy and it's at E and a smallest vertex cover. So the smallest vertex cover is a bunch of vertices. Some of those vertices could be in X, some of these vertices could be in Y. So the highlighted set here, you should think of them as the sets of nodes, a set of nodes in the vertex cover, right? Okay, and my goal is now to build a matching which is at least as big as this vertex cover. So let me call these two parts as A and B. So A is the part of the cover that is in X, and B is the part of the cover that's in Y. And what I'm going to show you is to build a matching which is as big as this. I'll show you a complete matching from A to the complement of B on the right hand side, and a complete matching from B into the complement of A in the left hand side. Okay, and then I can simply put these two matchings together into a matching of the entire graph. And clearly, since the matchings are in subgraphs which do not share any vertex, these matchings are guaranteed to give a matching when you put them together. Okay, so that's what I need to do to show a matching from A to Y difference B and from B to X difference A. I'm going to only do the first one, the other one is symmetric. So my goal is to show you a matching from A to Y difference B, a complete matching from A to Y difference B. Okay, and now remember, how can we show a complete matching? It says we can use Hall's theorem and show that there is no shrinking subset in A. There is no subset that's shrinking in Y minus B, right? Because the graph I'm trying to build a matching in only has A and Y difference B. So I have to show that no subset of A is shrinking in Y difference B. Okay, and similarly, I'm supposed to show that there is no shrinking subset in in B that is shrinking in X difference A, to show the part 2. But I'm going to focus on this first part. Okay, so I'll prove this by contradiction. Suppose there is some subset S which is shrinking in Y difference B. Okay, so let's so A has some neighborhood gamma A, and sorry, not A, S has some neighborhood gamma S, and let me consider removing S from the cover and adding gamma S into the cover. Okay, so I took my cover, which is A union B, that's C. I added gamma S into it, and I removed S from it. Okay, so that is this C union gamma S difference S. Claiming that there's still a vertex cover. Why is there still a vertex cover? Well, C used to be a vertex cover, but now I removed this S, so some edges became exposed. They are not covered anymore, but I'm adding gamma S, so every edge that was coming out of S is going into gamma S, and since I added all of gamma S into my new set, those edges are all covered. Okay, so all the edges remain covered when I remove S and add gamma. So it's still a vertex cover. On the other hand, I claim that it's actually a smaller vertex cover. So why is that? So remember I removed S, and so the new vertex cover has lost all those vertices, and they gained all of gamma S, but actually some of it was already in the vertex cover. It's only these new vertices which are in gamma S but not in B, right? Um, so the vertices in gamma S that are in Y difference B, they are the new ones I added. So the size of the new vertex set is, I have the original vertex cover minus the size of S plus only the size of gamma S difference B. Okay, so this gamma S intersection Y difference B. And since S is shrinking in Y difference B, this is strictly smaller than the size of S. So I have strictly decreased the size of this new vertex cover that I created. But that's a contradiction because I started with a smallest vertex cover. There could be multiple vertex covers which are all the same size, but they are supposed to start with one of the smallest ones. So there cannot be a strictly smaller vertex cover, which is what I have contradicted now. Okay, so it couldn't have been the case that there is a shrinking S, a shrinking in Y difference B, and therefore it satisfies the Hall's theorem condition to show that there is a complete matching from A to Y difference B. Okay, and as I said, similarly in the other direction, the part 2, and put together, I get a complete matching for I get two complete matchings in the two directions, and put together that's a matching of size C. Okay, which is what I wanted to prove. Okay, so that's Koenig's theorem, and so for bipartite graphs, that's all I wanted to say about vertex cover. It's essentially the same problem as matching. And in fact, even though I didn't show you, there is an efficient algorithm for going from the maximum matching to a minimum vertex cover also. So it's an efficiently solvable problem. But on the other hand, in general graphs, as I said, it's a hard problem. Finding a matching is still an easy problem, even in general graphs. Even when you have odd cycles, it remains an easy problem. Okay, and in fact, there is an even easier problem we can use for the purpose of finding a vertex cover, and that easier problem is to find a maximal matching. So it doesn't have to be a maximum matching. So what is a maximal matching? It's a matching such that you cannot add one more edge to this matching and keep it a matching. Okay, so if you add any other edge, any further edges into this matching, it would become not a matching. So every edge will intersect with some edge that is already in the matching. Okay, so to illustrate that, suppose we take this graph from before, and here is a maximum matching, in fact a perfect matching in this graph. Every node is matched here. But now consider this other matching. It has only 3 edges. So the perfect matching had 4 edges. Here we have only 3 edges. It leaves out 2 nodes unmatched. But you cannot add any more edges to it. There are several edges out here. You try adding any of them, they are going to say you try to add say this edge here that you cannot add without conflicting with this other edge already in the matching, right? So there's a maximal matching. In this example, you can easily see that because the only edge you could have added is the one here, and there is no edge there. So it's a maximal matching, and it could be strictly smaller than a maximum matching. Okay, and it's easy to find a maximal matching because you can. Here is a you just keep picking edges. until keep picking edges and add them to your matching. So to make sure you always keep picking, maintain a matching. When you pick an edge, remove all the edges that are that touch it, right? So if I say picked this edge, then I have to remove all these other edges here and here. Okay, and then pick another edge from the remaining. So this will be an edge I can pick, and then I remove all these edges, and then say I pick this edge. That will give me a maximum matching. At that point, I would have deleted all the edges, right? So it's very easy to find a maximum matching using a greedy algorithm. You may not, using this algorithm, may not find a maximum matching. But in fact, in this case, our interest is in finding a small maximal matching. Okay, so the greedy algorithm is in some sense better than trying to find the maximum matching. Okay, so why are we interested in finding a small maximal matching? That's because from a maximal matching, you can go to a vertex cover. Okay, so if I find, if I give you a maximal matching of size m, then it can be easily transformed into a vertex cover of twice the size of m. Okay, how is that? Simply, so in this case, these were the three edges. I simply add both the endpoints of each edge in the matching to my vertex cover. So my vertex cover has these 6 nodes, that is twice the size of the matching I started with. Okay, so that's a vertex cover. Why is it a vertex cover? Because if it were not a vertex cover, that means there is some edge that is not incident on any of these 6 edges. And then I could have added that edge into my so if it is not a vertex cover, then there is some edge such that both its nodes are not in C, and I could have added that edge and obtained some matching which is larger than n. Right? I could have added that new edge to the matching n. Okay. So if m is maximal, there is no such edge I could have added, and that means every edge is covered by these 6 nodes that I picked here. Okay, so another way to say that is if you found the smallest vertex cover and some maximal matching m, I'm guaranteed that C, the size of the smallest vertex cover, is less than or equal to twice the size of the maximal matching. In fact, because the smallest vertex cover is smaller, at least is no bigger than the vertex cover you found here. Right? So the smallest vertex cover is less than or equal to twice the maximal matching. On the other hand, it's greater than or equal to, its size is greater than or equal to every matching, in particular this maximal matching m. So I can bound the size of the smallest vertex cover within a range of factor 2 by finding a maximal matching. And in fact, I can improve the lower bound a little by finding the maximum matching here. And if I manage to find a smaller and smaller maximal matching, I can improve the upper bound a little bit also. Unfortunately, it so happens that finding the smallest maximal matching is also NP hard. It's also a hard problem. But in any case, it's not guaranteed that the vertex cover is the size of a maximum, is twice the size of a maximal matching. But this is a reasonably good approximation in many cases that you might be willing to work with. Instead of finding the smallest vertex cover, find as small or as easy a maximal matching as you can find, and simply include both endpoints of the maximal matching into your vertex cover. Okay, so that's an efficient algorithm that approximates the size of the smallest vertex cover. It gives you such a vertex cover up to a factor of 2. The last thing I want to mention about vertex covers is its connection with another interesting problem called the independent set problem. Okay, so what's an independent set? It's a set of vertices. It's a subset of vertices such that there are no edges which are completely within this subset I. Another way to think about it is if you took the vertex and deleted all the other if you took the set I and deleted all the other vertices, then you would not be left with any edges. Okay, there are no edges that are fully contained within I. So remember, edges. Each edge is simply a set of two vertices. So the set that set should not be contained completely within I. Okay, that's the condition for I to be an independent set. And it's easy to see that an independent set and its complement is a vertex cover, and vice versa. If you take a vertex cover, its complement is an independent set. So to illustrate that, here is a vertex cover from earlier. So the highlighted edges nodes here from the vertex cover. So I'm just going to draw this a little differently so that you can see all the vertex cover nodes on one side and its complement on the other side. And this being a vertex set means every edge is coming into this set here. Okay, there cannot be an edge which is completely uncovered, not between, not including at least one vertex from the vertex cover. So that's the same as saying the remaining vertices here form an independent set. Okay, so all I'm saying essentially is that a consequence of this fact that an edge not being contained in a set I means, remember, edge is just a subset of vertices. If it's not contained in the set I, that's the same as saying it spills over into I's complement. So the edge intersects with I's complement, and so I being an independent set means for every edge E, this condition holds. E is not fully contained in I, which is same as saying every edge intersects I's complement, which is same as saying I's complement is a vertex cover. Okay. So in particular, the size of the smallest vertex cover is n minus the size of the largest independent set. You find the smallest vertex cover, its complement will give you a largest independent set, and vice versa. You find the largest independent set, its complement will give you a smallest vertex cover. And clearly, one problem being hard makes the other problem also hard. Okay. And going back to our picture here, so we already talked about the relation between the vertex cover sizes and matching sizes. And what we just now said about independent sets is a different relation. It says that the range of possible values of independent sets is, if occupies the other end of this line. So if the smallest vertex cover is of a certain size, then n minus that will give you the size of the largest independent set. And in particular, if you have smaller and smaller vertex covers, you will have larger and larger independent sets. And there is, of course, the independent set plus the matching size of the largest matching cannot be larger than or equal to n, because for this independent sets to grow larger, the vertex covers have to grow smaller, and then the matching sizes will have to correspondingly grow smaller. Okay, so that's a connection between independent set sizes and matching sizes. Today I'll talk about an important class of graphs called trees. So let me just tell you what these are. So I'll define trees and forests. So a tree, if you look at this picture here, as the tree grows, one important feature of a tree is that once it branches out, the branches don't go back and join again, right? They stay as two different branches going forward. So if you were to think of the tree as represented by a graph, where all these nodes are, think of them as points in the trunk where the tree is bifurcating or trifurcating. And the important feature of this graph, well, one thing is that it's connected. So you can start from, say the root of the tree here and go and reach any other point in the tree. And also, there are no cycles. So this is the part about the tree not going and the two branches, not going and connecting back. Okay, so that's what we will define as a tree. It's simply a connected acyclic graph, a graph without any cycles, which has a single connected component. And we'll define forest as a collection of trees. So it is simply an acyclic graph. It doesn't have to be connected. Instead, you can have multiple connected components, each of which is a tree. So each connected component of a forest, it's connected and it is acyclic because there are no cycles in the whole graph. There is no cycle in any connected component. So each connected component in a forest would be a tree. Okay, so you could have something like this, right? So this is the whole thing here is a forest with 1, 2, 3, 4, 5 connected components, each of which is a tree. A forest could have a single tree, a single connected component. That could also be a valid forest. And so we'll see a few useful properties of trees and forests. So the first one is that if I took a forest and considered any subgraph of the forest, so remember, to get a subgraph, I would delete some nodes and edges. And by deleting, I don't create a cycle. So if I started with an acyclic graph, it will remain an acyclic graph. So if I took a forest and created a subgraph, it will remain a forest. If I took a tree and did that, it could get disconnected. So it may not remain a tree anymore, but it will still be a forest. Of course, I could take a forest or a tree and take a subgraph, which is a tree. That is entirely possible. Okay, but in general, what I can say is that any subgraph of a forest is guaranteed to be a forest. Okay, so going into the anatomy of a tree, an important notion is that of a leaf. A leaf is simply a node which has degree 1. So in these nodes, they have just a single edge incident on them. So they're all the green ones here are all leaves. Okay. So technically, leaf is simply a node with degree 1. I claim here that every tree with at least 2 nodes has at least 2 leaves. If I don't insist on 2 nodes, there is a counterexample, a tree with a single node. So it is a valid tree, it's acyclic, it's connected, but it has no leaves. It has a node of degree 0, it has no nodes of degree 1. So that would be an exception. But if the tree has at least 2 nodes, then I'm claiming that it has at least 2 leaves. So why is that? So let's think of a maximal path in the tree. So any graph, any finite graph, has a maximal path. This you could define by picking an arbitrary node, and if it has a neighbor, pick its neighbor, and then if it has another neighbor, not the one you already picked, pick that and keep picking until you cannot pick any more neighbors, and then come back to the node where you started from and repeat this again. So you might um, start from some node like this, pick its neighbor. In this case, if there's only one neighbor, you go all the way up to here, then you come back here and pick some other neighbor of this one, say this one, and then you keep going, arbitrarily picking neighbors until you get to a point where in a general graph you may not be able to extend a path because all the neighbors, all the remaining neighbors, either there are no remaining uh, you know or there are no remaining neighbors that were not already picked. Remember, we are trying to pick a path, so we cannot repeat a node. So you stop, when you cannot pick any more nodes which are not already being picked. Okay, so this is something you can do in any finite graph. It will end. It'll have to end because you're picking fresh nodes each time. There are only finitely many nodes to pick from. And when you have ended, you know that for every node that you picked, um, you know, either that node already has two edges that you picked from it, so you cannot pick a third one, or it is something for which all its neighbors have already been picked. Okay, so you can convince yourself that those maximal paths are defined in any finite graph. So let's pick one such maximal path, v0 to vk. Well, one possibility is that the path has only a single node, so k equals 0. But if k equals 0, what that means is this node v0 is an isolated vertex. It has no neighbors. If it had any neighbor, you could have extended the path by picking it. So, but if it is an isolated vertex, and if the tree has at least two nodes, then we have a contradiction because it'll have at least two connected components. It won't be a connected graph anymore. So, since the tree is connected and it has two nodes, this cannot happen. Okay, so the path is at least of length. It has at least two nodes in it. Now, I'm going to claim that the endpoints of the path have to be leaves. Suppose they were not. In particular, suppose V0 is not a leaf. Well, it has one neighbor here, V1. And if it's not a leaf, it has at least one more neighbor, okay, some other node V. Now, why am I not extending the path? So there's a maximal path, so I cannot add V to the left of this and make it a longer path. The only reason is because V already has occurred in this path. Okay, so this other neighbor of V0, if V0 is not a leaf, it has another neighbor, and that neighbor is already in the path Vi as Vi for some I greater than 1. So it already has one neighbor, which is V1. It should have at least one more neighbor, and that neighbor already appears as Vi in this path. But then I have a cycle here, V0, V1 up to Vi, and then coming back to V0 is a cycle. Okay? So it cannot be the case that in a maximal path, this endpoint has degree more than 1. Okay? So similarly for the other endpoint. So these are the two leaves that I can find from any maximal path in a tree. Of course, if it's not a tree, then these need not be leaves. There could be cycles. Okay. All right. So it's a very useful. It's a simple fact, but it's going to be very useful, especially combined with the next property. The next property says that you give me a tree with at least two nodes. Then we said it has at least two leaves, in particular at least one leaf. And suppose I deleted that leaf. Okay, so I deleted an arbitrary leaf W, deleted the leaf and of course the one edge incident on it. I get a subgraph. I get an induced subgraph of G. And the claim is that that subgraph is also a tree. Okay. So why is this? So I need to make sure that it is connected and acyclic. It's acyclic, and I cannot introduce cycles by deleting a node. And why is it connected? So consider any two nodes UV other than W in the original graph, originally, since the graph was connected, there was a path from U to V. Okay, and I'm claiming that any such path would be there in G prime too. Okay, why would it not be in G prime? If this path passed through W, then it won't be in G prime. If it does not pass through W, then all the nodes and therefore the edges between them are all present in G prime also. So the only way a path could go missing in G prime is if it passes through W. But it cannot pass through W because for that it has to enter W and leave W. There have to be two distinct edges incident on W, but W being a leaf has only one edge incident on it. So as long as U and V are both different from W, all those UV paths are retained in G prime. So every pair of nodes U and V other than W, of course, are connected in G prime. They remain connected in G prime. So G prime is also a connected graph. Okay, so G prime is also a tree. All right, so why is this such a useful, these two things, why are they such a useful fact? They're useful because you can use them for induction. Okay, so we have been using induction usually with numbers, with inducting on sizes of things. But here we can do an induction. It's again induct. We are going to induct on sizes of trees, but we can do the induction in a careful way by staying within the set of trees, by deleting leaves from a tree to get another tree. So let me illustrate that with a result here. The useful result in itself, it says that in a tree for any pair of nodes UV, there is exactly one UV path. Okay, and I do allow the possibility that U and V are the same node, in which case I'm claiming there is exactly one path, only the trivial path from U to itself, path of length 0. And yeah, so for any pair of nodes, possibly the same, there is exactly one path connecting the two, one path in the tree. Okay. So here, just to illustrate that, suppose I took some arbitrary U and V here, and you can look at the tree and see that, oh, there is indeed a path connecting these two nodes, and that's the only path. Okay. So how do you know it's the only path? Because suppose there were another path, you could see that this forms a closed walk. Right? You put together these two things, you will get a closed walk, and without retracing any. I mean, you're not retracing exactly the same path. Okay, so that would give you a cycle. So that's informally that's the argument that in an acyclic graph you cannot have two ways to go from U to V, because put together that would imply the existence of a cycle somewhere. Okay, but let's prove that rigorously by induction. And we're going to induct on the number of nodes, but as you'll see, we'll use the structure in the tree in terms of leaves. Okay, so the base case is simple. There's only one node. So the statement is about that one node here, and it has only one path from that node to itself, namely a path of length 0. Now suppose the claim holds for trees with up to k nodes, or with, exactly k nodes, for some k greater than or equal to 1, and we will prove that the claim holds for trees with k plus 1 nodes, right? So give me an arbitrary tree with k plus 1 nodes. I'm going to delete an arbitrary leaf W from that tree and get a new tree G prime. Okay, so here I actually used both the claims from the previous slide, that first of all there is a leaf So this is a tree with at least two nodes, right? K plus one nodes where k greater than or equal to one. So it has at least two nodes, so I can delete a leaf. So it has a leaf, so I can delete it. And when I delete the leaf, what I'll get is a tree, not just a forest.